Hello everyone. This is the solve paper for October 2024 IAL Chemistry Unit 5 from Edexcel Exam Essentials. Here we begin with section A. The first question says, what is the electronic configuration of the chromium atom? So in chromium, we know chromium has 24 electrons since the atomic number of chromium is 24. So we have the argon atom, and then so argon ends with 2d6, 2d10, and then 3s2, 3p6. This is where argon ends. Then so we begin with the 4s orbital. So 4s and 3d4, that sums up to 24 electrons. But as we know, for chromium, since the d orbital has only 4 electrons and one orbital is completely empty, one electron from the 4s orbital will go to the last orbital of d, just so that it is more stable, since a half-filled unpaired electrons are more stable this way. So in total, our configuration becomes 4s1 and 3d5. So our answer is B. Question 2 says, which ion shows the typical property of transition metals by forming colored complexes? Okay, so we know that color is only visible when electrons transition from lower energy orbitals to high energy orbitals, when there is a gap between the energy of the orbitals, of d orbitals. So we just have to see which of these ions have unpaired electrons in their d orbital. If we look at copper plus would have 3d10. This 4s1 will go away, so it has no incomplete orbitals. If you see at nickel 2 plus, it has 3d8, so there are two unpaired electrons. For sc3 plus, it's basically an a argon atom, so it doesn't have, since argon is a noble gas, so it doesn't have, it has a fulfilled last shell. And then Zn2 plus also has 3d10, since the orbital is fulfilled, 3d orbit, the subshell is fulfilled, so it doesn't have any unpaired electrons. So our answer is nickel. Number 3 says the formula of a chromium compound is this. The molar mass of the compound is 230.5. What is the percentage by mass of chlorine in the complex ion? Okay, so here the complex ion is this part, only this part, excluding the chlorine ion. So if we calculate the percentage, so we have two chlorines here, so 35.5 times 2 equals 71. 71 divided by the total was 230.5, but if we exclude this chlorine atom, so 230.5 minus 35.5, if we divide this, we get 0.364, which is 36.4%. So our answer is C. Number 4, the reaction between peroxide disulfide ions and iodide ions is shown. This is the equation. The reaction has a high activation energy, but it is catalyzed by iron 2 plus ions. What is the best explanation for the high activation energy of this reaction? So we know that iron 2 plus is catalyzing it. That means that iron 2 plus will, in this reaction, iron 2 plus is reduced to iron 3 plus, and then again, iron 3 plus reacts with iodine to form iron 2 plus. Since it's a catalyst, it will remain unchanged at the end of the reaction. So our option A says the peroxide disulfide ion is a weak oxidizing agent. It doesn't explain why it has a high activation energy. Oh, the iodide ions is a weak reducing agent. It still doesn't explain why the activation energy is high. Peroxide disulfide ions and iodide ions are both negatively charged. Yes, that is one reason. Since they are both negatively charged, they repel each other, which is why it's hard for them to react. You need to provide energy for them to react, to come close to each other. Which property of iron 2 plus ions enables them to function as a catalyst for this reaction? Okay, so as I've told that iron 2 plus is first reduced and then oxidized to uh, uh, become iron 2 plus again. Therefore, the answer is C, that iron 2 plus ions can be easily oxidized and then reduced. Oh, I'm sorry. In this equation, at first it is oxidized since it's losing electrons, right? Since it's losing electrons, oxidation number is increasing, since so it's oxidized at first and then reduced. Chromium 3 hydroxide is amphoteric. This means that chromium 3 hydroxide dissolves in, since it's amphoteric, this means it can behave both as an acid and a base. That means it will dissolve in both in an acid and a base, since when it is reacted with a base, this compound becomes an acid, and when it is reacted with an acid, this compound becomes a base. So it can react with both a strong acid and a strong alkali. The answer is D. Naphthalene is an aromatic molecule with two aromatic rings joined together. It can be nitrated at position 1 as shown. Okay, in this experiment, 2 gram sample of naphthalene was titrated and produced 2.57 gram of this. What is the percentage yield of 1 nitronaphthalene? Okay, so the mass of nitronaphthalene is 2.57 grams. Therefore, I can find the actual mole that of 1 nitronaphthalene that is produced. So it would be 2.57 divided by the molar mass. We get this. Since it's a 1:1 ratio, reaction is 1:1. That means the amount of mole of naphthalene that reacts will produce the same amount, or the mole of 1 nitronaphthalene. Therefore, mole of naphthalene would be the same as this should be, but since we have 2 gram, we were given in the experiment 2 gram sample, so we can find the actual mole of naphthalene, which was this. So therefore the theoretical mole should have been, okay, sorry, I think I made a mistake somewhere. This is the actual mole of nitronaphthalene. Okay, yeah, so my given mass was 2 grams of naphthalene. So I found the actual mole of naphthalene. If this exact amount of naphthalene were to react to form 1 nitronaphthalene, I should have got this amount of naphthalene, which is the theoretical mole of nitronaphthalene. But what I got this one, this much. Therefore, the yield is the actual value, which is this much, 0.148555 divided by this value, 0.015625 times 100. We get A, 95.1%. Student carrying out this experiment calculated the percentage yield of the reaction to be greater than 100%. What is the most likely explanation for this result? Okay, so the student got an yield of more greater than 100%. That's unusual. So what could be the case? Okay, A says that there was unreacted naphthalene present. If there was unrated naphthalene present, then the yield would have been lower than 100%. It doesn't explain why it's more than 100%. If some of the naphthalene does not react, if it remains like this, then the yield is obviously below 100%. The naphthalene was impure. Same logic. If it was impure, that means some of the naphthalene is not reacting. Therefore, the yield should be less than 100%. C says the sample of 1 nitronaphthalene was damp. This could be the reason, because if you look at D, other isomers of 1 nitronaphthalene were produced. So different isomers of the same product doesn't affect the yield because it's the same product. So yield would have been the same as what we found, 95.1%. So since A, B, and C does not explain why the yield was greater, C must be the answer by process of elimination. Number 7, this question is about the azo dye, which has a structure. This structure is shown in the production of chrysoidine. Phenylamine is first reacted with nitrous acid, which equation shows the formation of nitrous acid from sodium nitrate. Okay, sodium nitrite reacts to form nitrous acid. We know nitrous acid is HNO2 and sodium nitrite is NaNO2. So if we look at this, NaNO2 plus HCl should produce HNO2 plus NaCl. This is the correct equation. In this equation, we have sodium nitrate, not nitrite. In this equation, we have nitrite, but our product is Na plus a half Cl. This is not produced. Na always reacts with Cl to produce NaCl. So our answer is A. The reaction of phenylamine with nitrous acid produces the benzene diazonium ion. Which is the structure of the benzene diazonium ion? Okay, so obviously the ion's structure is this, because the plus positive charge is with the nitrogen that is directly bonded with the benzene group, because you can see that nitrogen is already bonded with four electrons are bonded, only one electron is left, which it loses to the Cl or any other ion, and so it forms the positive ion. Which reactant is required for the coupling reaction with the benzene diazonium ion to form? Okay, the reaction that is required. Okay, so we found this is the part of the diazonium ion, so we would only need this, like this part, right? This NH2, and we have NH2. This compound is required. From here, the hydrogen leaves and the diazonium ion gets bonded. So A is our answer. Next question. The amino acid serine has a structure shown. The IUPAC name for the serine is okay. So in IUPAC style or by the rule book, you have to start naming the carbons from where the carbon is double bonded. So since this carbon has a double bonded with O, this is the number 1 carbon. This is 2 and this is 3. Therefore, our naming would be, since number 2 carbon contains the amino group, 2 amino. Number 3 carbon contains the hydroxy group, so 2 amino, 3 hydroxy, and since there are 3 carbon chains, so it will be propanoic acid. Since this is the carboxylic acid group, so the propanoic acid term, hydroxy comes from this, and amino because of the NH2. B, which is the organic product of the reaction between serine and sodium hydroxide solution? Okay, if this reacts with sodium hydroxide solution, then this is gonna form the ion where it loses this hydrogen, so it becomes CO minus, and then an Na plus could react with it to form COONA. Here we have A is the answer, and only the carboxylic acid group reacts with the sodium hydroxide, since the alcohol does not react. The Cumin process is the main industrial method for making phenol. Okay, what is the atom economy by mass of the Cumin process for making phenol? Okay, we can find the atomic economy. So here we have 6 carbon atoms, so 6 times 12, plus 1, 2, 3, 4, 5 hydrogen atoms. And if we count this one, so 6 hydrogen atoms plus 16 for the oxygen, and in total, this is the MR of this product. It gives us, let me calculate, 6 times 12 plus 6 plus 16 comes to 94, and the total MR would be this 94 plus the MR of this substance. So we have 12 times 3 plus 16. Okay, so we have plus 12 times 3 plus 16 is 146. Therefore, our percentage is 94 divided by 146 times 100. 94 divided by 146 times 100. This gives us 64.38. So this is 64.38, and it seems we don't have the answer here. So I must have made a mistake somewhere. Oh, I did not count the hydrogens here. So there are six hydrogens in total. I should add six to it. So 146 plus six is 152. So this would be 152. So this should come around at 61.8, which is approximately 61.8%, which is approximately 62%. Then we move on to question number 10. An aromatic compound with a 10 carbon ring has a structure shown. Okay, evidence for the aromaticity of this compound is that the carbon-carbon bonds in the 10 carbon ring. Okay, since for it to show aromaticity, the pi bonds, this pi bonds should delocalize, must delocalize like the benzene one. Like the benzene should form a delocalize and form a ring with where each of the bonds has the same length and same bond energy. Basically, each of the carbon environments are equal. So A says alternate in lengths between, like it cannot alternate lengths, all the lengths must be equal. All have similar lengths, so we have the answer B. C says have no regular pattern of bond length. It has a regular pattern of bond length in benzene, and all similar to the carbon-carbon double bond length. No, it's not the similar. They are very different from carbon-carbon single bond and carbon-carbon double bond. This type of bonds are different from this two bonds. The aromaticity is due to the formation of pi bonds as a result of overlap of p orbitals, because we know that C double bond, when it forms, that this pi bond is formed by p z orbitals, so it's always the p orbitals. Number 11, the polymer nylon 610 is made from a 6 carbon diamine and a 10 carbon dicarboxylic acid, which is a repeat unit. Okay, for this question, we need to understand that for the diamine, 6 carbon diamine means like it has an amine in both its ends. So here I have CH2. How many times? There are 6 carbons, so 6. And then and at this end, it is another amine group. This is okay. But for the carboxylic acid, since 10 carbon carboxylic acid means the carbon with the carboxylic acid group with the COOH group, this carbon is counted, right? Here in the amine, it's connected to the carbon, so we can write as 6 chains. But here, this carbon is counted along in the 10 carbon group. So here is a carbon, and then there is COOH. So we had 10 carbon atoms. I've already drawn 2, so what is left is CH28. There we go. So we need to find CH26 and CH28. 8 has in both its ends has COCO, while 6 at both its ends has NHNH. So our answer is D. Car exhaust gases react on the surface of a catalytic converter. Which interactions could not occur between the gases and the catalytic converter in this process? Okay, so covalent bonds could react, because in the catalytic converter we know adsorption happens, and covalent bonds could be broken down during absorption. London forces might occur. This is a very this occurs all the time. So London forces might occur, and permanent dipole-induced dipole forces can occur, um, because the catalytic converter could be like, charged, and so permanent dipole-induced dipole forces might it can also occur. But hydrogen bonds are one bond that will never occur, since none of them has like hydrogen in them, and also none of them are like polar compounds. Therefore, it's B. Number 13, which pair of equations shows the most likely mechanism for vanadium 5 oxide acting as a catalyst in the contact process? Okay, so in the contact process, we know that the vanadium is first reduced and then oxidized. So therefore, V2O5 will be reduced by sulfur dioxide to V2O4, and then this V2O4 will be um, recuperated with initial form by oxidizing it with oxygen. So since it's the catalyst cannot change, its initial condition and final condition should remain the same, V2O5. So this is what happens in the other equations. This doesn't happen. The formation of carbon dioxide from the reaction between manganate 8 ions and its entire 8 ions is catalyzed by the manganese. Okay, a lot of things is told, and which I've asked which graph for the complete reaction shows the autocatalysis of this reaction by the manganese ions. Autocatalysis means as the reaction proceeds and more manganese 2 plus ions are formed, the reaction will go much more faster since the concentration of this Mn2 plus ions increases. So it would give a graph like this, where at first it's like slower, the reaction is slower, and then it suddenly increases because as the concentration of Mn2 plus ions increases, and then it reaches a plateau where the reaction is complete. Okay, so this ends our part section A of this paper. I will see you in the next video where I solve the section B. This is the beginning of section B of the 2024 October IAL Chemistry Unit 5. So if you look at the question number 15, it says this question is about butylamine. The boiling temperature of butylamine is 78 degrees Celsius, which is much higher than that of alkanes. Okay, butylamine is miscible in water. Okay, so since it's soluble in water, you draw a level diagram to show that the intermolecular interaction between butylamine and water molecule. Okay, so you can see that butylamine has the structure of this 1, 2, 3, 4, and then NH2. So this alkyl group is an electron donating group. So basically, this entire compound is a polar compound. Since here it's del negative, sorry, this is del positive and this is del negative. It's a polar compound, and so is water. So, and since they all, both of them has like hydrogen, they can form hydrogen bonds. So the only intermolecular forces will be the hydrogen bonding between the NH. This N is partially negative since this carbon or this alkyl group is donating electrons, and then since it's negative, and also nitrogen is more electronegative, which pulls away the electron from the hydrogen, so the hydrogen becomes partially positive, and this hydrogen forms a hydrogen bond. This is hydrogen bond, hydrogen bond with the partially negative oxygen of the water molecule. Then besides, what butylamine has a fishy ammonia-like smell. The exposure limit or safety level for the in the atmosphere for butylamine is 15 milligrams per cubic meter. Okay, so I must to calculate the maximum number of butylamine molecules that are allowed per cubic meter. Okay, so I have 15 milligrams per cubic meter, so I can find out the mole, which is 15 times 10 to the minus 3 divided by the MR of butylamine, which is 73. This equals to this. This is the amount of moles that is the limit for me. Therefore, I can find the amount of molecules by multiplying the mole with the Avogadro's constant, and I get this value. Then butylamine reacts with ethynyl chloride to form butylethanamide. Okay, okay, I have to display the formula. So this is butylamine, butylamine, and this is ethynyl chloride. This is ethynyl chloride, and so basically what happens is that this hydrogen breaks down and this Cl goes away. Both of these form the hydrogen chloride, and this gets joined with the NH, forming a amide group. Amide group. Simple reaction, we all know this. Explain why butylamine is stronger base than ammonia. As I've said, that the alkyl group attached to the amine is electron donating, so it donates the electron to the nitrogen, which increases the density of the nitrogen atom in butylamine. Therefore, so since the density is greater than that of ammonia, which only has a lone pair and has no like it is not partially negative. So, since the electron density in butylamine is greater, it's more likely to attract a proton and bond with it, form a coordinate covalent bond. Iron is number 16. So iron is generally prescribed a person with anemia. Okay, and iron solution advertised for this purpose contains Fe2 plus ions. Okay, an adult is advised to take 90 milligrams of iron daily, and we have a 25 cubic centimeter sample of the solution, which was made up to 100 cubic centimeters. So 25 to 100 cubic centimeters, which means um, if I calculate for the 100 cubic centimeter, I will have to uh, eventually take like 1/4 of it to find this. And then, okay, so if the 25 cubic centimeter sample solution was made up to 100 cubic centimeter using sulfuric acid and water, 25 cubic centimeter of this 100 cubic centimeter was then taken and was titrated with this concentration of potassium manganate, and the volume was found this. So I have the volume and the concentration of the potassium manganate. I can easily find out the mole of the manganate ions, this one, and I found this. So this is the mole of the manganate ion, and from the formula, I can see that the mole ratio, the reaction ratio for manganate ions and iron 2 plus ions is 1:5. Therefore, the mole of iron 2 plus ions would be 5 times the mole of manganate ions. So, which is this. So, what I found this is the mole of iron 2 plus ions in what? In 25 cubic centimeter of out of which was taken from 100 cubic centimeter. So, the mole in 100 cubic centimeter would be 4 times that of what I found in 25 cubic centimeter. So I multiply it by 4. This mole times 4. I find the mole of iron 2 plus in 100 cubic centimeters. So this was what actually this is the amount of mole that was actually in this initial 25 cubic centimeter solution. Therefore, if I find out the mass from this mole, I get that the mass is 226 milligrams. So apparently I have like in 25 cubic centimeter solution, I have 226 milligram. I need 90 milligrams. Therefore, it's easy to find out if unitary method, the volume I require is 9.96 cubic centimeters. Okay, we move on to the next question, question number 17. This question is about electrochemical cell. Describe how you'd carry out an experiment to determine the standard electrode potential of the electrode system shown. Okay, assume that you have access to the equipment and chemicals that you need, describing their use. In your answer, you may include a level diagram. Okay, so we can find out the electrode potential of these. How is it found out? So we basically take a standard hydrogen electrode on one side and then connect it with the my desired like my desired solution. So here's the standard hydrogen electrode, and this is my like cobalt, cobalt solution. These are like what do I say, like copper. It could be copper, it could be cobalt. It's up to your wish. So basically, yeah, but since the electrode is cobalt, I would suggest that it use cobalt electrodes. So the electrode is cobalt. It's a wire connected with this. It's a platinum electrode because we use platinum since it's like it doesn't react with the hydrogen. Here we have HCl solution, and a salt bridge. So this is the basic formula. This is the cell plus minus, and a voltmeter is connected in parallel. So what we need for the standard hydrogen electrode, we need a concentration of 1 mole per cubic decimeter at 1 atmosphere and 25 degrees Celsius, which is room temperature. The salt bridge could be used, like KNO3 could be used. You can also use other um, compounds, but it's like normal to use KNO3. Most of the time we use KNO3 or NNO3, stuff like that. And then the cobalt solution should also be standard concentration, so 1 mole per cubic decimeter of cobalt solution. Since we are using the salt bridge is KNO3, so we need that nitrate radical, so cobalt nitrate could be used as a solution. And then that's it. This is the diagram, and it's just like the V cell would be, so the voltmeter reading is the E cell of cobalt, that's the electric potential. Uh, yeah, that's it. We move on to the next question. Sorry, it's taking a little bit. Okay. Acidified potassium dichromate is an oxidizing agent. The acid is commonly used in sulfuric acid. Okay. Then explain what using reference to the electrode potential shown why concentrated hydrochloric acid should not be used to acidify potassium dichromate. Okay, so you can see here, right? So I am asked to use I'm asked that why I cannot use concentrated hydrochloric acid, which means, so concentrated hydrochloric acid means the concentration of Cl minus is greater. So I cannot use this at higher concentration to acidify this one. So basically acidify meaning that this becomes, this is the reverse equation, which means it's oxidized. Okay, it's oxidized, so I cannot use it to oxidize this. Why? Because um you can see oh no, sorry, I'm wrong. Like acidified potassium dichromate. So this is the dichromate. So this is the reduction. I cannot use it to reduce this equation. So since I want to reduce this equation, so this has to be oxidized, right? So this has to go in the reverse direction. So if I calculate the E cell of the value, so what's the equation? Equation for E cell is reduction minus oxidation. Reduction minus oxidation, and this equals to, the reduction is 1.33 minus 1.36, it's negative 0.03. So the E cell value is negative 0.03. So it's the reaction is not feasible. All right, the reaction is not feasible. But if I increase the amount of like chlorine, okay, if I increase the concentration of this Cl minus, the value becomes smaller, right? So this value gets down, gets smaller. Since the value is very small, so I've written like, since the value is very small, using concentrated acid reduces the chlorine electric potential. Therefore, the reaction becomes more feasible, and therefore chlorine gases will be produced. Okay. And the next question is, the cell diagram for an electrochemical cell is shown. Okay, right, the reduction half equation. So the reduction, right? Uh, for here the reduction, so Ag is turns from Ag to Ag plus. Silver loses an electron, so losing his oxidation. Therefore, the reduction is the reaction for VO2 plus. So VO2 plus plus H plus, the given equation. Since it's being reduced, so it will gain an electron. So I write one electron, and then so it becomes VO2 plus. Why only one electron? Because here the um, oxidation number of V of vanadium was what? It was 2 to the 4 minus 4, so it was plus 5, and here it is 2 plus 4, right? So the oxidation state reduced by 1, therefore it has to gain 1 electron. D, the direct methanol fuel cell uses methanol, whatever it's spoke about, random stuff. Write the oxidation half equation for this fuel cell of what? So methanol oxygen to generate electricity. When the cell operates, the methanol reacts with water at one electrode to produce carbon dioxide and hydrogen ions. So it will produce carbon dioxide and hydrogen ions. And I'm asked to write the half equation. So yeah, so methanol reacts with water to produce carbon dioxide and hydrogen ions. How many hydrogen ions? Since we have like in total of 3, 4, 5, 6 hydrogen ions. So six hydrogen ions are produced, and to produce these hydrogen ions, from this equation they need to lose 6 electrons, since there are 6 hydrogen ions. So I can either write minus 6 E minus here, or I can just write plus 6 E minus here. It's the same thing. write the overall equation for this fuel cell. Okay, so what's happening is basically it's the methanol is being combusted. So methanol reacts basically reacting with oxygen. So CH3OH plus O2, it produces carbon dioxide and hydrogen just to just balance the equation. The reduction half cell in DMFC has a standard electric potential. So E cell is given 1.23, and then I have the change in the electric potential to 1.20. This is my Nernst equation, like a version of the Nernst equation, where X is the concentration of the solution in mole per cubic decimeter. Calculate the value of X. Okay, so I just input the values of it. So E is 1.20 and E cell is 1.23 plus 4 point this and ln X and then normal arithmetic equation, and I have this. Don't try to round this number up, keep it as it is, like up to like 4 decimal places is fine. Then we have number 18. The question is about color transition metal complexes. Okay, so the iron 2 plus ligand complex ion is green, but the iron 3 plus complex ion is yellow. Yes, explain why they have different colors. Okay, so these ion or this ligand complex ion is colored because iron 2 plus has a d orbital, and the d orbital has unfulfilled d orbital actually. So that unfulfilled d orbital splits into two different energy orbitals. One is a higher energy, one is a lower energy. So basically what happens is the electrons in the lower energy, they absorb the photons of light from light, they absorb the photons and gain energy, and then they can jump from the lower energy orbital to the higher energy orbital, like this is the lower energy, this is the higher energy orbital. So electrons from here can jump to here by absorbing photons. And then when they're come down, they can radiate the absorbed energy. They radiate the absorbed energy, and then they come down to their initial state. So this is called when they go up. This is called the excited state, and this is the normal state. So they come down to the normal state by radiating the absorbed energy. So this radiation actually gives rise to the color because the color actually depends on the wavelength of the radiation, right? And th wavelength of the radiated energy. So this is the explanation that I've written. Explain why the two iron complex ions are different colors because the energy gap between them are different. Since one is 2 plus and the other is 3 plus, so the energy gap between their higher energy orbital and lower energy orbital will be different, and therefore different wavelength of photons will be absorbed by the two electrons, and therefore the radiated wavelength will be different. Okay, number B, it's the question is about the thiocyanide ion forms in red blood cell colored complexes. Okay, this is the structure that is given. Complete the alternative what? The dot and cross diagram for the thiocyanide ion can be drawn in more than one way. For example, the negative charge on the nitrogen atom as shown. Okay, so this negative charge can be like drawn in another way. Since it's a linear compound, there is only one scope for the negative charge to go, which is with the sulfur ion. I am asked to like complete the alternative dot and cross diagram of the thiocyanide ion where the negative charge is on the sulfur atom. Yes, it's on the sulfur atom since the negative charge is here. That means the extra electron which we have, which we are denoting by this triangle, is in the sulfur atom. Before it was with the nitrogen atom, but then now it's with sulfur. And there, this electron which is unpaired before is now bonded with the carbon atom now, and sulfur loses one bond. So here it's one bond, and there is a triple bond between C and N, and so it's basically you have to find out that you have to balance out the electrons to figure out the structure. Okay, 12.2 says 12.8 cubic centimeter of this concentration of iron 3 chloride solution reacted with 8 cubic centimeter of this concentration of ammonium thiocyanide to form a complex ion. Deduce the formula of the octahedral complex ion. Okay, so I must do. Okay, so we can find out the mole ratio of the reaction. So I can find out the mole of Fe3 plus ions from this volume and concentration, which is this, and also the mole of SN with thiocyanide ion, which is also this. So I can, so since both the moles are equal, that means the reaction is 1:1. So 1 mole of F3 plus ions will react with 1 mole of HCN minus ions. Therefore, I can say that there is a one Fe3 plus and one SCN minus. They react to form FeSCN, and the charge will be reduced from 3 plus to 2 plus, since this is 1 minus, so 3 minus 1 is 2. But initially, I had like six oxygen molecules bonded, six oxygen molecules bonded with the iron. Since now one thiocyanide ion has been added, so it will displace one water molecule. So there will be five water molecule left, and this will be the required ligand. Then we have calorimetry, which was used to determine the concentration of a solution of copper sulfate. Six solutions of copper sulfate. I'm given a table, and then I'm asked to plot a graph of absorbance, which is this values, with concentration. So I can, since concentration is like independent of the absorbance, so I will have to put concentration in the x-axis and absorption in the y-axis, and then if I plot a graph, it will be a straight line, as you can see. And then I'm asked, okay, then number two, 50 cubic centimeter of solution of copper sulfate and of unknown concentration was prepared into a 250 cubic centimeter volumetric flask, and the volume made up to the mark with ionized water. The absorbance at a wavelength of 365 nanometer for this diluted copper sulfate solution was 0.72. So I know the absorbance. So for 0.72, which is here, I can find out that it would be 0.26. So since I know that it's 0. Wait a minute. Yeah, so when I know it's 0.26, so I know that the diluted copper concentration is this. Therefore, I can find out the how many moles are there in 250 cubic centimeter. So 0.26 times 250 by 1000. Therefore, the original concentration would be, so this is like in 250 cubic centimeter. So what would be in 50 cubic centimeter? I can just divide it this by this and left with this, and I get the original concentration. Number three, give one possible reason why any concentrations of copper to sulfate determined from the graph of values over 0.5 are uncertain. So in the graph, we actually don't have any value over 0.5, so we don't have the data for 0.6 mole per cubic decimeter or 0.7 mole per cubic decimeter. So we cannot be sure that after this point the graph remains straight, or the graph remains linear. It will become this or like this. We don't know for sure, okay? So which is why the values we obtain after this will be uncertain. Number D, the complex ion formed from cobalt and ethane 1,2-diamine is orange, yellow and orange color. Okay, this. Give a reason by referring to the equation why the formation of the diamine complex from the aqueous complex ion is thermodynamically favored. Okay, you can see that here in the reactants, the total amount of mole was 4, 1, and 3. And for the product, the total amount of mole produced is 7 moles. So I get like from this reaction more moles, okay, more particles are produced. So since this more particles are produced, therefore there is more what would I say, like more disturbance. So since there is more disturbance and more randomness, the entropy increases. And since entropy increases, this equation will be thermodynamically favored. Explain by reference to the structure of ethane 1,2-diamine why it is a bidentate ligand. It's a bidentate ligand because we have like two nitrogen atoms here. So you can see that here, if I draw here, there are two nitrogen atoms, each having like a lone pair, which these two lone pairs are available to form dative covalent bonds. And since they are much farther apart from each other, they can cover like two, like what's it like cobalt. They can cover two bonds. Here one N, here one N, and like this is long enough. The bond is long enough. Therefore, it can form like two. Uh, it can act as a bidentate ligand. Explain how an H and H bond angles would be expected to change. Okay, so in here, if we look at the structure here, we had a lone pair, LP, and 1, 2, and 3, three bond pairs, right? So for the N, in the ligand, for the N, we had one lone pair and three bond pairs. Therefore, since that the repulsion between a lone pair and a bond pair is greater, the angle was 107 degrees. But after forming the complex ion, this becomes a bond. Therefore, N now has four bond pairs, which therefore, since the repulsion between bond pair is the weakest, so the angle actually increases to 109.5 degree, much like CH4, like methane, right? It becomes tetrahedral in shape, and the rest you know. Then we have section C. We move to section C, but before moving on to section C, I would like to mention that you can join our high impact crash course here in Edexcel Exam Essentials. So you'll what we'll get in the crash course, you'll have the solve paper for all the recent papers, like from January 2020 to May 2024, all the solved question papers, and you will like your asked frequently asked questions will be answered, and you will get the full syllabus will be reviewed and recorded topic based, and you'll get like recorded like this one topic based videos, and also like tips and tricks for the exam. So don't miss out this chance. Stay connected and sign up to our Facebook page, which is Edexcel Exam Essentials. You can search it up. So don't miss this chance to see achieve your dream grades and in your L levels or O levels. And this is especially good news for the May 2025 candidates, since don't have much time left. If you're still struggling, please sign up to our Facebook page and contact our tutors. They will be there for you to, they will help you to reach your goals. Okay, if we move on to 19, question number 19. This is about the ketones, the raspberry ketone. Okay, so I've asked that over 200 different compounds contribute to the smell of raspberries, including the one known as raspberry ketone. This is the formula, displayed formula. Raspberry ketone is also found in other fruits, such as cranberries. It can be extracted from the fruit present, okay, and in a very low percentage, and so it's prepared industrially by a variety of methods. The two-step method shown gives a 99% yield, okay? Then two other compounds are also formed, which is this alpha ionone and beta ionone. So what is the empirical formula for raspberry ketone? Okay, so we can see that in raspberry ketone, there are like in this ring, there are um, six carbon atoms. So 6, 7, 8, 9, 10. So 10 carbon atoms. We have two oxygen atoms, and in total of 12 hydrogen atoms. If you count 1, 2, 3, here we have 3, then 4, 5, 6, 7, and 8, 9, 10, 11, and this one 12. So this all three values can be divided by 2, and then we can find that there are 5 carbons, 1 oxygen, and 6 hydrogen. Therefore, the empirical formula is C5H6O. Then we have question B. Okay, question B. A raspberry ketone can be synthesized in a laboratory from phenol using a Friedel-Crafts reaction. The overall reaction is shown. Okay, draw the mechanism for this. Okay, you are asked to draw the mechanism. It should be quite easy for you now. So here we add aluminum trichloride or AlCl3, which actually uh, what to say, it acts as a catalyst, and this takes away this chlorine atom. This chlorine atom gets attached to this one, and it forms this electrophile, right? This electrophile, and then this electrophile is attacked by this benzene or like phenol from via the pi bonds, and then it gets bonded with this one. This is the intermediate that is formed, and then this hydrogen loses the electron to give to fulfill this what to say, like the pi bonded ring, uh, and then and H plus is formed. This H plus is then reacts with the LCl4 minus, since it's a negative ion, so the LCl3 remains and HCl is formed. So the since LCl3 is the catalyst, the initial condition and the final condition are the same, so it goes back to its initial state. Then we have number 2, give a reason why the yield of raspberry ketone by this method is not high. Okay, it's not high because the substitution, like for this to form this, like this molecule needs to be bonded in this exact position, right? In this exact, if we count like from here, 1, 2, 3, in this fourth carbon atom, it needs to be bonded. But in this reaction, we cannot control where this bond will get added. So it could be like in here, in here, in here, in here. So there are lots of isomers that will form along with this compound, which is why it doesn't have a very good yield. Okay. The raspberry ketone can also be synthesized in the laboratory using a Grignard reagent via multi-step process. Okay, we can use a Grignard reagent. The overall reaction is shown from here to here. You can see that along this OH becomes O, and another chain, another methyl group is added, right? Methyl group is added. So this is where we're gonna need the Grignard reagent. So since only one alkyl group, like a methyl group, is added, we're gonna need a methyl bromomethyl CH3Br, and make it react with solid magnesium, and this will create CH3MgBr, which is our required Grignard's reagent. And then we take this compound and then a small amounts of K2Cr2O7. So we need small amounts because we don't want this to oxidize too much, because if it oxidizes too much, it will create COOH, carboxylic acid. We don't want that. We just want an aldehyde. So we take this and an aldehyde is formed. This aldehyde then can react with the Grignard's reagent, CH3MgBr, and what happens is this O becomes OH, and this chain, this alkyl chain, gets attached in this bond. As you can see, this is the CH3, and the rest of the components form. You don't have to mind that, whatever forms. So we have this, but we can't have this alcohol. We need a ketone. So for that, we can use and again oxidizing agent like K2Cr2O7, or you can use any other uh, really powerful oxidizing agents, and which form, since it's a secondary alcohol, it will form a ketone. Here we have our required compound. Number D, the second step of industrial preparation of the raspberry ketone involves the reduction shown. Okay, it's been reduced to H2 catalyst. Here H2 has been added. Suggests why the choice of reducing agent is particularly important in this reaction. Okay, so I cannot use too much of a powerful reducing agent, because if I use a too powerful reducing agent like LiAlH4 or something like that, it will actually reduce the ketone here. It will reduce the ketone to an alcohol, and so therefore I cannot use strong reducing agents. The alpha ion and beta ion molecules are structural isomers. Yes, because like here you can see that they are. Um, wait a sec. Yes. Here you can see like there is a double bond, there's a double bond. So like there, since here is an H. So there are sorry, not cis, trans isomers. They are trans isomers, stereoisomers. Wait, it's clear, but what I'm asked is compare and contrast the stereoisomerism of these two molecules. Yeah, so both are trans isomers along this double bond, but only alpha ion has a chiral carbon. Yes, you can see like this is a chiral carbon. This is a central carbon atom bonded with four separate different groups. Therefore, it is a chiral carbon. But this beta ion doesn't have that because here it's a double bonded. A chiral carbon cannot have a double bond. Therefore, neither is this, neither is this. So there is no chiral carbon here. Therefore, this is the only difference between them. Identify with an asterisk the carbon atom environment in alpha iono, which would be expected to produce a peak with a quartet. Okay, we need a quartet, right? That means by the n minus n plus 1 rule, so 4 minus 1 would be like we need 3, like, right? We need three hydrogen atoms bonded to adjacent carbon atoms. So say if we are looking at this carbon, the adjacent carbon atoms, like this carbon atom must have three hydrogen bonded with it. So we are looking for a carbon atom which has adjacent carbon atoms bonded to it, and these adjacent carbon atoms must have like in total of three hydrogen atoms bonded to it. So say this carbon atom has two hydrogen, and this carbon atom has one hydrogen. So in total, we have three hydrogen atoms. This configuration will actually give us a quartet. So here in this molecule, we only have this single carbon atom, if you can say like this single carbon atom. So see, this carbon atom is bonded with this adjacent carbon atom, and this carbon atom has only one hydrogen bonded with it, and this carbon atom has two hydrogen bonded with it, because like two bonds are already there, so the rest two are hydrogen, and here three bonds. Therefore, only one bond left for the hydrogen to react. So we have three hydrogen atoms, which will give us the required configuration of a quartet. Predict the number of peaks in the carbon-13 NMR spectrum of beta ion, which has the molecular formula of C13. Okay, so basically, the peaks are formed due to different carbon environments, and every single carbon here, you can see like every single carbon here has a different environment. Like this carbon here is bonded to this, and this carbon is bonded to this. So none of the environments are equal. Environments will be equal only if there is a symmetry, right? Only if there is a symmetry, but there is no symmetry in this compound. But we can see that these two ethyl like CH3 groups, these two CH3 groups are bonded with the same carbon atom, so therefore they must be in the same environment. This carbon atom is also bonded with this carbon atom, which has the same configuration, like it's a ring, a cyclic compound. And this CH3 is also bonded to this carbon atom. Therefore, they are in the same carbon environment. Therefore, they're the only two identical. Therefore, they will give only one peak for this both of the CH3 groups. There will be only one peak. Therefore, since there are 13 carbon atoms, and we reduce one, because for this two I will only have one peak, therefore there will be 12 peaks. And okay, this is the end of our paper. I hope you understood everything. I hope you don't have any confusion, but even if you have, you can check out our page at Edexcel Exam Essentials, and we will